Fantastic.
Sorry for the delay. So,
Okay, so the final talk in this session, Matthias will be telling us about dependently typed data plane programming.
okay, hi everyone. I'm Matthias from TU Darmstadt in Germany. And in this talk, I'm going to present you our work on dependently typed data plane programs. This is joint work with Eric Campbell, Matthias Krebs, Mira Mezzini, Nate Foster. So let's start by having a look at a piece of code inspired by a network router. When a packet arrives, we start parsing the packet. And during this process, we read bits from the packet and store them in a type representation. First, we pass the Ethernet header. Next, we look at the ether type field of that header. And if the field contains the value 0800, we continue parsing. If it's not the case, then we're done. Assuming the value is 0800, then we continue with the parse IPv4 state, where we read the IPv4 header in addition, and then we're done with parsing. In the next step, we check if the packet origins from some specific IP address. And if that's the case, then we discard the packet. The program shown here is written in the P4 language. And with the P4 language, it's possible to specify the behavior of network data planes in software. The data plane is responsible for forwarding network packets, and it's often comprised of specialized hardware that's capable of efficiently forwarding network packets. Programmable data planes open up a whole new range of applications, ranging from new network protocols up to moving application logic into the network. Unfortunately, P4 has a semantics that makes it easy to introduce subtle bugs. For example, let's consider the following path through the program that a packet with an ether type different from 0800 would take. In the ingress, we try to read the IPv4 source address, even if the packet does not contain an IPv4 header at all. But it's not the case that there will be an error. Instead, reading the IPv4 source address will provide some random value, which could be equal to the IP address by accident, leading to the packet still being dropped. Of course, there's much more to the language, but more generally, P4 is based on a pipeline abstraction consisting of 3 stages: a parsing stage, a transformation stage, and a deparsing stage. Given an input packet, it executes a sequence of blocks of code, 1 per pipeline stage. The parser is a state machine that maps binary packet into a type representation. But before we can parse any packet headers, we have to first define the structure of headers and which headers the program should operate on. We're calling the latter header instances. Let's assume our parser extracts both instances A and B in this order. Then it copies the bits at runtime from the packet into this memory location, while the remaining bits provide the payload. As seen in the code example, not all predefined headers must be populated, so programs often define many more headers than a single packet might carry. In the next stage, we compute transformations on packet headers, and in this example, we are simply updating the contents of header A. And finally, we write headers back into a new packet that is then sent out, and this process is called deparsing. As illustrated by the example, P4 lacks even basic safety guarantees, and in practice, programs are, of course, much more complex, which increases the risk for introducing bugs. Since networks are critical infrastructure that provide the communication fabric for the majority of today's software systems, we want to statically check that data plane programs are correct. Of course, we are not the first to do that. There's quite some interest in statically verifying the correctness of P4 programs. Existing verification tools are, for example, based on symbolic execution or predicate transformers. But these approaches are monolithic in nature and therefore lack the support for compositional verification. This worked well in the past, but more and more people start to look into composable approaches to data plane programming. As a consequence, we need compositional verification methods. And luckily, we have type systems that are a lightweight and compositional way to establish program properties. Types allow us to capture assumptions components rely on and the guarantees they offer. So let's build a type system for P4. We have a couple of requirements for our type system. First, we want to be able to reason about values being manipulated, as programs rely on intricate packet formats, where often the first few bits determine the type, length, and structure of bits that follow. Second, we want to have precise types that are able to statically capture the effect of domain-specific language features, such as parsing on the program state. Third, we not only want to annotate precise types, but also retain them during type checking. For example, for conditionals, types should cover both branches. And finally, we want automated subtyping checks in the style of PWS or Liquid Haskell, where subtyping checks are backed by an SMT solver. So we propose Pi4, a dependently typed core of P4, which captures the essence of the P4 language, but provides a combination of expressive types on top. Compared to P4, Pi4 provides a more uniform syntax. It's an imperative language with a few domain-specific commands for parsing and deparsing, adding and modifying header instances, and a reset command, which resets all assumptions about valid headers. We assign a dependent function type to commands, and intuitively, the input type describes the program state before the execution, and the output type describes the resulting program state after executing a command. And using a dependent function type, where the output type can reference the input, allows us to relate both program states. We refer to program states as heaps, and correspondingly, we provide heap types that allow us to capture the state of a heap in a type. Here we combine dependent pairs, union types, refinement types, and explicit substitution. Accordingly, the semantics of a heap type is a heap consisting of the input and output packet, as well as valid header instances that can be safely exited. Let's see how type checking in Pi4 works, using extract as an example. Here we are extracting an Ethernet header. Before we can type check, we of course have to define a type. Again, our input type describes the heap before the execution. And here we say that no header instances are valid. The input packet provides at least 112 bits, and part of the input packet is known. After executing the command, we expect the Ethernet header to be valid, and the ether type field contains the value 0800. As you might guess, the value of 112 in the input type was chosen intentionally. It corresponds to the number of bits that an Ethernet header comprises. Let's demystify the typing rule. In P4, parsing a header is only possible if enough bits are available in the input packet. And accordingly, we first have to check the side condition that our input type provides enough bits, or basically that the input packet described by the input type provides enough bits. As mentioned before, the Ethernet header comprises 112 bits, so we have two 48-bit fields for the destination and source address, and 16 bits for the ether type field. If we look at our input type, we see that the condition holds, since we stated that we expect the input packet to have at least 112 bits. We use a sigma type as an output type, and semantically, the sigma type describes a dependent concatenation of heaps. So, for example, if we have two heaps, one where instance A is valid and one where another instance B is valid, then the resulting heap contains both instances. And for the input and output packet, we simply append the bit vectors. For example, the output packet in the first heap contains value 1, 1, and the output packet in the second heap contains value 0, 0. So the result of the concatenation is 1, 1, 0, 0. And the intuition behind the output type is the following. We take the heap on which only the extracted instance is valid, in our example, Ethernet. And here the refinement states that the input and output packet are actually empty for this heap, which means we don't want to add additional information in our packets. And then we concatenate this heap to another heap we obtain from the input heap. And here the general idea is that this type reflects the removal of the first n bits of the input packet, where n corresponds to the size of the instance. And the refinement phi2 captures this intuition. The instance added to the input packet of the resulting heap is equal to the the instance added to the input packet of the resulting heap is equal to the input packet of our initial heap. And the output packet, as well as all other instances, remain unchanged. the computation of this resulting type is done by a refinement transformer that we defined, which is called CHOMP. We've heard, so in our example, CHOMP syntactically transforms our input type such that the resulting type captures that the first 112 bits of the packet are moved into the Ethernet instance. And to achieve this, CHOMP updates all refinements referring to the input packet. In today's keynote, we've heard about Brozovsky derivatives. And if we recall our heap types, we notice that we have a combination of different types, including regular types. And what's effectively happening here is that CHOMP computes a Brozovsky derivative for the input type. So if we look at our input type, then the first reference refers to the length of the input packet, which says it's 112 bits. And so the result of our CHOMP operation would remove the 112 bits of this refinement. And the second refinement refers to a known part of our input packet, and CHOMP takes care of moving these bits into the instance Ethernet. And the slice from bits 96 to 112 exactly correspond to the ether type field. And this is what the final type computed by the type checker then looks. And the only thing that remains is to check that the computed output type is a subtype of the output type we have annotated, which is the case here. As I said, we want to enable modular reasoning, and as such, it's not sufficient to be able to check if a program has a certain type. Instead, we need a way to annotate and modularly check programs, which we achieve by using a type description operator. An ascribed type indicates a program point where type checking should occur, and this allows us to independently type check a command at some type. We can then rely on this type to check the rest of the program. For example, let's consider the following code snippet, which resembles the parser from our initial example. And using type description, we can now annotate the program with the type we wanted to have. For example, we might only be interested in the guarantee that the Ethernet header is valid, and we don't care about the rest. This is expressed by the following ascribed type. If the code is executed in a context where no header instances are valid and enough bits are available in the input packet to extract both Ethernet and IPv4, then it's guaranteed that the Ethernet header will be valid afterwards, but possibly also headers we don't care about. One of our requirements was to have automated subtyping checks without the need for programmers to provide additional proofs. But when we look at the following type, we notice that the input packet is constrained in the subtype, but not in the supertype. This means that the input packet can actually be arbitrarily long. And of course, the same applies in general to the output packet. However, network switches have a maximum number of bits they can receive or transmit, which is called the maximum transmission unit, or in short, MTU. When a P4 program is compiled to a switch, we know that the transmitted packets must be smaller than the MTU. And we can exploit this fact to prove a bound on the size of bit vectors that must be considered. So here we say that a type tau is bounded by n in a context gamma if for every environment that's compatible with the context and every heap and the semantics of the type, the length of the input packet plus the length of the output packet must be less or equal to n. We can then use this fact to formulate a decidability theorem, which states that if types in the context, the input and output type, as well as every ascribed type in command C are bounded by the MTU, then checking command C in context gamma with type tau1 to tau2 is decidable. We implemented our type checker in OCaml and used Z3 to perform subtyping checks. And in our implementation, we encode subtyping checks into a formula in the theory of fixed bit vectors, basically using the trick we pulled with the decidability to achieve that. We have two frontends available. We can either check programs written in the DSL presented in the paper, and we can also check real-world P4 programs using using a P4 front end. And here we are relying on P4's annotation mechanism to annotate and check types. However, this is still work in progress, and not all of P4's language features are yet supported. Our type system is capable of expressing a wide range of interesting properties. For example, we can check that dependencies between headers and field values are correct. For example, if the ether type is 0800, then an IPv4 header must be present. We can also check that protocol invariants follow specifications. For example, the so-called time to live field of an IPv4 packet is 0. So if it's 0, then the packet must be discarded. And finally, we can check that specific headers may not be present in a packet at the same time. And now we'll look in more detail at this property. So in general, we want our network device to be able to handle all kinds of network packets. And since we have to define all headers the program will use up front, it's pretty common that not all defined headers will be present in a single packet. For example, a packet will never be an IPv4 and IPv6 packet at the same time, while our network switch should be capable of processing both protocols. If we know this statically, then the compiler can use this information to perform optimizations. For example, use the same memory location for both headers. The following code snippet shows how we would parse an IPv4 and IPv6 header depending on the value of the ether type. Here it's easy to see that the property holds, but in larger programs it might not be that trivial, especially if we conditionally add headers at some point in the program. We can express this property, for example, with the following type. This type states that if we start in a state where no headers are valid, but enough bits are available to parse Ethernet and IPv4, respectively IPv6, we end in a state where at least Ethernet is valid and IPv4 and IPv6 are never valid at the same time. In the paper, you find more involved examples that demonstrate what Pi4 is capable of expressing. To summarize, we have seen what data plane programming is about. We looked at Pi4, a dependently typed core of the P4 language, which provides a combination of expressive types, which allow the programmer to express and check rich network properties. We've also seen how type checking in Pi4 works, using the example of an extract command. And with the help of the predicate transformer CHOM, we are able to precisely track the result of parsing in a type. We've also seen that type checking is decidable, which we achieved by exploiting the fact that network packets are bound by the MTU. And finally, we've looked at a couple of properties we can check. Of course, I couldn't fit everything into this presentation, and you'll find all the details about Pi4 in our paper. So thank you very much for your attention, and now I'm happy to take your questions.
Do we have any questions?
Hi, I'm excited to hear that you have a P4 front end that works on real-world programs. Have you happened to deploy this on some example programs? And if so, can you characterize how well it worked for those examples?
Yeah, so actually, what we're using for the front end is the Petra framework that was presented last year at POPL. Internally, we are compiling to our internal DSL, meaning currently it's not all of the language features are supported, so it's still a bit of work needed to check full programs like the well-known switch.p4, but for smaller to medium-sized programs, this works quite well.
Are there any other questions? All right, we have an online question. Can you speak about the precision and scalability of your type system?
Can you maybe clarify that question a bit more?
how
Okay, I see. Yeah. Well, actually, so in general, the P4 programs we have checked so far are yeah, rather small, and a real evaluation on yeah, large programs is still on the to-do list, basically. Um, so we still have kind of yeah, difficulties with scaling the subtyping checks. Basically, the longer the programs get, the more complicated get our encodings, um, leading to yeah, longer type checking times, basically. And we're still working on that. But to give you a rough idea, so we checked larger programs with around, I don't know, roughly yeah, 50 commands, and this basically type checks in a couple of milliseconds.
see y'all at lunch.